Thanks to those of you who came to the last number 3 seminar of the semester. We're happy to have Shilin Lai talk about other systems in the twisted Friedberg-Jacquet setting.
Okay, thank you for the invitation. It's good to be back. Okay, today I want to talk about the twisted Friedberg-Jacquet setting, Euler systems. Everything I have to speak about will be joint work with Simonyi and Yangyu. So to start with, I'm going to recall the unitary Friedberg-Jacquet period. In this case, I'm going to reserve for here for the fields. We are going to start with the CM extension. F0 is totally real, F is a CM. Then we consider unitary group G, a unitary group in two variables. Defined with respect to the CM extension. And H is going to be a product of two unitary groups, and we assume the spaces are this space is the direct sum of those two spaces, so there is a natural embedding. And that pi.
Is there any signature, or are there
currently any signature? I'm going to restrict to the usual one soon. So pi is going to be automorphic cuspidal automorphic representation of GL2N of the base field. And we are going to assume it's symplectic. Which concretely means its adjoint L function has a pole at s equals to 1. Assuming this is expected. Okay. If pi is symplectic, then you can consider the base change of pi from F0 to F, and then we can transfer pi to the unitary group G. IG automorphic rep of G in F0 with the same base change as pi. With same base change to F as pi. Then we would expect that the H period of IG is non-zero. This should be related. This is not true, but I'm going to explain that. This should be related to the central value being non-zero. Approximately equivalent to that. Okay. This is kind of the standard philosophy, at least, that the normalization of a period should be related to an L value. But the reason this is only of approximate equivalence is, first of all, already in something like the GGP case, I can't just restrict to a single unitary group. I have to consider all pure inner forms of the unitary group. So a real statement should at least say the central value being non-zero is equivalent to this H period being non-zero for a specific inner form G and H. That's already in the GGP case. In this case, it's even more complicated. Due to the need to consider inner forms beyond the pure inner forms. So to make this precise, we need to already introduce the twisted setting. And so I'm going to follow the notations of Spencer-Leslie, Jingwei Xiao, and Wei Zhao. Okay. So what those group did is they introduced a biquadratic extension. So we have originally a CM extension here. We are going to introduce a totally real extension by a totally real quadratic extension. Then take their composite terms. This is biquadratic. There's a third quadratic field. And this middle extension is CF. Okay, that's the field diagram. The more precise conjecture is H period of pi g is non-zero for some inner form of H and G. If and only if two different L functions, one of L of 1/2 base change I'm not going to specify what kind of inner forms show up. Those are not pure inner forms. They are unitary groups of certain quaternion algebras. And the exact definitions can be found in their preprint. And another thing of interest is it's not just a single value, it's two L functions, but it's not that both of them are non-zero, it's one of them is non-zero. And this twisted setting naturally shows up if you try to use the relative trace formula approach to even study the untwisted setting, because this shows up in the stabilization process. Okay. So the goal of today is to try to study some kind of arithmetic picture of this. So even in both untwisted and twisted settings, assuming you impose the right signature condition. So in the untwisted conditions setting, we use the signature where G is U 2n minus 1, 1, and H is U n minus 1, 1. So we are imposing it to be have this signature at one Archimedean place of F0 and compact at all other Archimedean places. And in the twisted case, you impose something similar to it. In this case, we have Schumann varieties. H embedded into Schumann variety of G. This has dimension 2n minus 1. This has dimension n minus 1. So we get a special cycle. In the arithmetic middle dimension, so this is codimension n tau group of Schirmer Q. And this statement is just true in both the twisted and untwisted case. I just don't want to tell you exactly which quaternion algebra, which unitary group we are talking about. Okay, so to the automorphic representation pi, we can attach its p-adic Galois representation. Rho pi going from Galois group of F0 to GL2N. Let's just use QP1. And this appears, or this is expected to appear in the cohomology, in the Etal cohomology. Of the Schirmer variety of G. So not necessarily this representation, but at least its restriction to the smaller Galois group, Galois over F. So restrictions, rho pi restricted to Galois F will appear in the Etal cohomology of the Schirmer variety of H. And our question is, so if you follow through with the usual philosophy of translating from period statement to arithmetic version, you would say maybe the height of this special cycle should be related to a certain L derivative. We are not going to make such a conjecture. This is already quite intricate on the period side. So we are just going to ask the question. The question is, extend this base class, this special cycle Schirmer H, maybe the pi-isotypic component to Euler system. Or rho pi. And I'm going to define what I mean by an Euler system more precisely.
A Selmer group floating about?
There is a Selmer group floating about, which will come here when I define what an Euler system for me is. Okay. So just to fix ideas, I'm going to state a main zero. Zero, this is a result. Here is split anticyclotomic Euler system. For not the representation of rho pi, which in the twisted case is not the natural object that shows up, but for the first of all, we restrict from F0 to E, and then induce it from E to F prime. F prime is the middle CM field. And if you write it out, this is rho pi restricted to F prime, direct sum, rho pi twisted by the quadratic character, restricted to F prime. So we have an Euler system for the direct sum of two representations. Each of the summand is exactly one of those L factors that shows up. So this is some kind of arithmetic version of that. I will not say what I mean by that, but this visually resembles that. And what do I mean by a Euler system? Whose base class is what I said earlier. Is Shimura H projected. Just to be clear, this is in H1 F of F right. I'm going to call this representation rule just from now on. So more precisely, for each place L, each place L of F0, which splits in F prime. So split anticyclotomic means we are looking at the CM extension F prime over F0 and only considering the split places F prime. So for each split place, there exists a class, let's call it ZL in H1 where here this is a ring class field. Conductor L. So we have classes over anticyclotomic abelian extensions of F prime satisfying the norm relation.
What do you mean by anticyclotomic?
And
F prime is a CM field.
N prime is a CM field.
It has R2 plus 1 ZP extensions, ZL extensions.
Yes.
Okay. What's the anticyclotomic one? There are lots of them.
I'm working over.
Yeah. A non-cyclotomic one.
Yes.
Okay.
I'm.
Yeah.
All I'm doing is I'm working over all of them.
All of them.
I'm working over all of them. Yes.
But you are
Now, so I'm working over all of the ring class fields. So away from this. Yes.
away from the cyclotomic one.
Yes.
Yeah. Okay.
So all of the dimensions that are conjugate axis minus one.
So if geopole is true, you have an R2 of them in this.
Yes.
Okay.
But really, we are just going to be working over one place at a time. So
No, I understand.
Yes.
I understand.
but the point is we have classes over all ring class fields. Satisfies, and this should really be for a fixed integral lattice. The point is I don't want them to have arbitrary denominators. I fix an integral lattice and require all of my classes to be in them. The exact choice doesn't matter, but it has to be fixed upfront, such that the co-restriction of ZL is this base class. Let's just call it Z. But with a certain Frobenius acting on it. Here, EL T is the characteristic polynomial. and unramified. And by Frobenius, I secretly mean we fix one of the places of f prime above L, take that Frobenius. So there is a choice of a place above L. Yeah. This that I'm hiding in the notation. And this is arithmetic, so this is geometric Frobenius. The actual definition of Euler system, you are allowed to take a couple of different primes L, but this is kind of already is enough.
Is it more like a polyvariant system?
This is
Rubin and Mason.
this is more like a Kolyvagin. This is more like an Euler system as defined by Kolyvagin,
So not the polyvariant system,
but not
defined by Mason and.
but not a Kolyvagin system defined by Mason and Rubin.
I understand.
This is the split anticyclotomic Euler system was defined by Djachev, Griskinner, and Negovart.
Do you get the other layers of the Euler system, or do you just?
I get all the layers. I just can't be bothered to introduce
But
notations.
this is enough.
This is not just you.
Yeah.
This gets the idea across. You get all the other layers too. Okay. So the source of all ZL and all the higher layers is highly translates of the embedding Shimura H into Shimura G. So first, I'm going to just reduce this problem of constructing those higher classes. Okay, I'm going to reduce the problem of constructing those higher classes to one that's purely functional analysis, harmonic analysis. Then we are going to solve that harmonic analysis problem. So it's know that there is a map going from all smooth compactly supported functions say with GP coefficients. There exists a map to a Chow group. I'm not going to. The dimension is yes. Worksheet with CP coefficient. This is not strictly speaking correct. Well, I don't know standard conjecture, so this is not correct. We use some Itoku homology realizations of it. Well, let's not go into that detail. And this is GAF equivariant. So here's a Schumann variety. G really means the inverse limit of also Schumann varieties. So this is the direct limit of a bunch of Chow group, a bunch of continuous Itoku homology groups actually. So it's known that there exists such a map going from test vectors on adelic test vectors on basically G mod H to special cycles on the Schumann variety.
The original cycle is constructed at finite level, right?
So all the cycles, all of them are constructed at finite level. So this is just a convenient way of packaging. So
if you just quotient it on the left by some finite, you could take invariant.
you would,
Version, right?
so if you have a K0, it will just be K0. This is just convenient. So the point is, there's a GF equivariant, and to get integer coefficients here, all all that you need is integer coefficients there. So integer valued function, ZP valued function gets mapped to ZP valued cycle. You do not introduce any extra denominators in this construction. And they are very standard Jacobi constructions, giving you elements here. Well, in this case, it's actually over F prime. Okay. This part is standard. I don't really want to talk about that more. So first thing to do is I'm going to explain how to get all the abelian extensions. So to get abelian extensions, take this augmented group. I didn't tell you what G is. You can keep on pretending it's U2N. And I'm going to cross a U1. And this is a F prime over F0 U1. So H embedded naturally. So to define this, I need to tell you the additional piece of data, which is a co-character of H. So once I have a co-character of H, I can define this augmented map. And the role of this co-character is really to tell you how to trace back characters. In this case, because I'm using U1, I'm looking at anticyclotomic characters. So you can continue using the same formalism. You get H mod G cross U1, CP valued functions, mapping to, this is just a collection of points. Schimmer variety of G times the Schimmer variety of U1.
Why do you want H again?
H is basically UN cross UN, but some inner forms of it.
For the extension F over F0.
So both of them are inner forms of unitary group for, yes.
So what does this character nu look like?
I'm going to tell you what it looks like in the local setting. So in the split setting, H is UN cross UN, the character nu is the quotient of the determinant.
Okay.
But I'm going to explain the local settings soon. So now the Schimmer variety of G is defined over F. This is defined. This Schimmer variety of U1 is basically the spec of the anticyclotomic extension of F prime. So once you fix a level here, you get Schimmer variety of G base changed to an anticyclotomic extension. So fixing U1 level here responds to taking anticyclotomic extension. So basically, the problem of constructing classes over abelian extensions comes down to, instead of studying G over H, studying G cross U1 over H, which on the functional analysis part doesn't change all that much.
But could you say this without the U1 just by keeping track of the field of definition of each component?
You probably can, and that's annoying to write.
Okay.
So
Yeah.
This is probably the nicer way to look at it. Okay, so now that we have all the setups, we wanted to construct some field that's defined over the ring class field with conduction L. That means the U1 level should be unramified everywhere, and just slightly ramified at L. And I never had to think about the G level, really. So really we want,
I think there's a more detailed, I mean, the answer that you gave, it's not just that it's more or sort of more problematic to keep track of the fields of definitions. It's actually from some of the harmonic analysis point of view. This translates the Galois action into.
yes, okay. Yes, okay, sure. I'm just going to ignore that point for now. But no, that's absolutely correct. Okay, but so we want to construct an element, let's call it delta L in this function space. So I'm going to just start with a fixed level structure on G, and the level structure on U1 will be the unramified everywhere, but at the place L, I'm going to force it to be in this instead of OL cross. Such that the trace of delta L and taking the trace from this 1 plus LOL to OL cross. So this is going to be in the same function space. So this is a trace of degree L minus 1. We want this trace to be basically this high-k polynomial times a basic element, which is just the indicator function of a maximal compact. Indicate. The indicator function of the maximal compact subgroup. So under this map, the basic element will be just that no high-k translate standard Schema variety special cycle. And this element under this map will be sent to the higher level class ZL. And this relation plus the common charisma is exactly going to translate to this co-restriction relation. Okay. So now we have translated everything to the construction of this element. And this is a purely local statement. Everything up there was identical. Now I'm just going to secretly pretend I have taken FL points. So let's look at the place L. So L was a place of F0 which splits in F prime. So now there are two cases, whether it splits in F or did not. So there is what's known as the split case, where L splits everywhere. Well, not everywhere, like all three fields. In this case, whether you are twisted or untwisted, the local setting is G is GLQN, H is GLN cross GLN. And the character nu is, since the matrices A and B to the quotient of the determinant. It's very important that this is a quotient. The product does not work. There is from basically local harmonic analysis, there is a good reason why the quotient doesn't work. Why the product doesn't work, there is a good reason why you have to choose the quotient. So in this case, the kind of delta L was constructed explicitly by Andrew Graham and Carr, and I think the published version is 2023. So in this case, this is the standard Friedberg-Jacquet model. There is a local zeta integral. They constructed the correct test vectors, verified it works using the zeta integral. And because of multiplicity 1, that relation must hold. And in our case, because we reduce it to a local picture, everything is still the same. So we don't really do anything. Well, we don't get anything new here. Our method is completely new, even in this case. The next one, which the LXZ group would call inert, case is L is inert in F. In this case, the local setting is a quasi-split unitary group over F0. The subgroup is restriction of scalar of GOF. And the character nu is just the norm of the determinant. In this case, we don't know any local zeta integrals for those pair of groups. In fact, the local multiplicity for the unramified restriction problem is 2 to the power of n. So we have no zeta integral, we have no multiplicity 1. We use a new method to prove the existence of this element directly. We use unramified Plancherel formula. And our method uniformly applies to both settings, provided the unramified Plancherel formula is known. Okay, so in the last part of my talk, I'm going to explain this approach. Are there any questions so far about this reduction step? So remember, there are two things. So I'm going to introduce some notation. X is going to be G, let's say, aeronatic points. I'm just going to write X as G mod H. There is a difference between F points of G mod H and F points of G mod F points of H. This is the whole reason we need to stabilize the trace formula in any case, but I'm going to ignore that. That doesn't really matter for us. So X is just going to be the variety. Then there is this vector bundle G cross U1, which because we are working at a split place, just becomes a GM. So this is a GM bundle. And remember, our local translation was looking for an element delta L in the smooth compactly supported function on X tilde with ZP coefficient. And here, because L is auxiliary prime, we are just going to keep it at the hyperspectral level at G. And the level on TM is still the same. We need to find this such that it's traced from 1 plus L or L invariant to OL cross invariant is equal to a Hackett polynomial times the basic element. So this is abstractly the problem statement. All the geometry is gone, it's just purely find a function in this test vector space. So now we have two steps. One, characterize the image of the trace map. So the image of the trace map would be surjective if this were QP coefficient. You should think L is, so this trace map is of degree L minus 1, you should think that's very divisible by P. So because it's CP coefficient, this is not going to be surjective in general. So we are going to give a characterization of this and still prove just the right-hand side is satisfies this.
If I were to make a naive guess, it would be that that image was generated by the PL of T times everything and then sort of the norm or the index. How close is that?
I don't know. So we didn't characterize it that way. Our characterization is very clear. It has nothing to do with P or anything like that.
Does it contain PL of T times every?
It does. That's the whole point. But that's actually just the goal of step 2.
So it contains what I was guessing.
It contains what you're guessing.
Not all of it, right?
I cannot say anything further than that because our characterization is completely separate from the PL stuff. So step 1 is we want to characterize the image of trace. Well, the image is lines in this function space. So the image lies in this function space. We are looking for a subset of this function space, which is just x tilde mod this open action. I'm not doing anything fancy here. So this is some space with a group action. We are modeling out by the action of the maximal compact subgroup. You get a discrete space. There is something called, well, I guess here, the generalized Cartan decomposition. The classical Cartan decomposition is basically the maximal compact acting on G cross. So G cross G acting on G would give you classical Cartan decomposition. This is generalized Cartan decomposition. It tells you this space can be canonically indexed by a torus, by a lattice, which in this case looks just like by a cone in a lattice, by a cone. All of them are integers. Yes. Actually, because X tilde always carries this GM bundle, there's always going to be some kind of completely unrelated set here. But generalized Cartan decomposition tells you that this space is just indexed by it. One of our proposition is the trace at least contains the element. We suspect this is an F but all we need is it contains all F such that contains all functions f such that f of this tuple of integers is divisible by L minus 1 if an is 0 and just no condition otherwise. So we prove that if you have a function which is divisible by L minus 1 on a specific wall, on this specific wall, then it's in the image of the trace. And all other n minus 1 walls doesn't matter. Only one wall matters. The way we prove this proposition is by exploiting the proof of the generalized Cartan decomposition by Gates-Green-Adler. We consider the asymptotic degenerations of these spherical varieties. Well, they exploited that to prove the Cartan decomposition. We considered x cubed over x, the degeneration of this EM bundle at infinity, and show that in quite a large generality, this kind of characterization always holds. And the difference for the experts are those walls are type T. This wall is type N. No, the other way. This is the only wall of type T. And all the other are type N. So we can prove that the trace at least contains all the functions that are divisible by L minus 1 on the wall of type T. So given that characterization, the second part reduces to show this PLT acting on basic element evaluated on one of those tuples where AN is equal to 0 is divisible by L minus 1. So this PLT is not given concretely as a double cosine operator. This PLT is given concretely by its static H transform. Is given by static H. So it's an annoying problem to even compute this PLT as a double cosine operator. So we bypass that completely. Theorem. This is due to Omer-Ofen in the split case. I guess Yana-Saglarides. In general, but not general enough to cover the inert case. And as but our method is basically just, okay, all of them use basically the same method. And our proof is just copying Ofen's proof at various points we need to change the sign. It's not anything particularly key. It's like a master's thesis level project. My collaborator described it. The theorem is there exists an isomorphism from this. Instead of CP, we are going to use C coefficient. So what you would expect is this would be L plus minus that I. And then there is the And then there's a torus piece, the S variable there. There's this one which is equivariant with under Sadake. And that looks different depending on whether you are in the split or inert case. But it's just Sadake, the convolution algebra G mod K mod K acts on this. And on this side, Sadake tells you it's the real functions on a torus, but that torus is different depending on whether you are in the split or inert case. And from this, you can already, if I write down exactly what I mean by equivariant under Sadake, you can tell that it's going to have multiplicity 1 in the split case and multiplicity 2 to the n in the inert case. Just because in the inert case, the Sadake isomorphism involves terms of the form L plus minus 2 zeta. And O. While invariant. And the while group is a type C while group. That's part 1. Part 2, which is more important, well, equally important, is there exists an inversion formula. Inversion formula. So if we have a polynomial L hat in the image, and I want to compute its inverse formula of the form L hat becomes interpreted as a polynomial, multiply it by a very concrete rational function. Restricted to lambda x plus. Okay, this requires a lot of explanation. So L hat, we view it is a function of the polynomial ring. So we can view it at the theorem includes the definition of this rational function, which is basically the Plancherel measure. Half the square root of it. Yes, this is basically the square of this will give you the Plancherel measure on this space. So this is also basically the value of spherical functions at specific elements. But in any case, we construct a very explicit concrete rational functions, multiply that by L hat. Now we have a rational function, which we expand in a Laurent series in L to the plus minus 1 along a certain cone. That is along a certain cone that is opposite of this cone. So lambda x is some cone like this. We have a Laurent series that's with coefficients always here. So if we restrict to lambda x plus, there should also say plus. So once we restrict to lambda x plus, I get a compactly supported function on lambda x plus, which is that function. So there is an inversion formula of this form. And all you really need is to specify this rational function. Then it's just the coefficient of a certain Laurent series expansion. Now you just need to compute a Laurent series expansion. Except I don't even do that. That's too much effort. So formally, it is easy to show coefficients are in Z, P. Well, they're actually integer coefficients. I'm allowed to invert P But inverting P is fine because P is co-prime to L. I do not know. I'm allowed to invert L. Coefficient is P. I'm allowed to invert L. That's completely fine. Yes. We can show formally that the coefficients are there, and we need to prove divisibility by L minus 1. So what we do is, so we specialize formula at L equals to 1. I'm going to write out the shape of this rational function in a maybe mysterious way. This integral kernel, this rational function, looks like a product of two things. In the numerator is some kind of co-roots. In the denominator, it's some kind of stuff. So first theory is going to be L to the power of minus 1/2 times some kind of, so gamma check and theta check are both some kind of very concrete co-roots that I don't want to write down. And this is plus or minus depending on whether I mean split or inert case. So it has this shape. And I'm not going to explain, I'm not going to give you the exact formula for this. The point is, first of all, this part has some subtlety where I need to prove that the L to the 1/2 cancel, so we get integer power of L, that's easy. Now the point is, if I specialize at L equals to 1, this becomes a product of 1 minus e to the gamma check over product of 1 minus, well, plus minus e to the theta check. The L to the negative 1/2 disappears, and most terms cancel. So after most terms cancel, there are a bunch of terms left. Remaining terms multiplied by the specific L factor. The specific L factor is a polynomial that we have been carrying around this whole time. Is a polynomial. So first of all, most of those terms already just cancel within the kernel. And now once I multiply by this L hat, all of the denominators disappear. And this polynomial is antisymmetric under a Weil group action. So this is easy. The denominator is completely written down. Yes, you just observe all the terms already appears in L hat. This, you just look at the shape of this resulting polynomial. It's visibly antisymmetric with respect to a Weil group, meaning if I apply a Weil reflection to the resulting formula, it changes sign. Under a Weil action, so under, let's be more precise, simple reflections. But it only changes signs if it's of type T. Simple reflection across walls of type T. If you do a reflection across the walls of type N, you do not change sign. It's symmetric across those walls and anti-symmetric across walls of type T. So this formally implies that its coefficient on a wall of type T is 0. And the coefficient is 0 means it's divisible by L minus 1. So that's how we prove part 2, which is this high K polynomial applied to the basic element satisfies the criterion established by part 1. So the kind of the distinction between walls of type T and that's not type T, that's type T, not that really means much. But so there is a dichotomy between type T and type G that's seen in both kind of this asymptotic geometry part and this harmonic analysis part. We don't know how to handle walls of the type N, but nobody does. So, okay, that's it.
Any questions? So what does the Euler system do for you?
Nothing. Well, I don't know.
Yeah,
I was asking you earlier, is the Zellman group with
It's
order you want to?
well, the series it's a row plus a row twisted by eta,
And
Euler system requires your rep to be irreducible.
yeah,
What if you project to one of them?
We talked about this. I don't. The whole point of this talk is not that we got an Euler system. The point is we got an Euler system. Stop asking questions. You do the rest. For the moment, yes. It's more like we have this new technique of doing things. Here's a case where we got something new.
Related question, what do you know about the base class?
Nothing.
Are there other possible cases where the new cases for this?
Yeah, so I'm working on incorporating other side series. So this recovers most of the previously known Euler systems, like the one for Bayes and Flach elements, all of the cycles stuff. So I'm looking for new cases invented by Chris. And we are also kind of looking at Cornu's case again. Cornu's case is orthogonal group embedded into unitary groups.
Other way around.
Other way around, yes. Yes.
Do you know if there's expected to be a formula for the Friedberg-Jacquet periods?
I asked Wei Zhao. He said, not yet.
It's not really an answer. Like, that means that maybe it's expected.
Well, if he doesn't know or refuse to tell me, I'm not going to guess. It seems to be more complicated because this is two different L functions show up. You are not obviously product way.
Thank you.
Any more questions? Now let's thank Leo again.